Now, last class was the introduction to nonlinear programming problem for you. There I have introduced the nonlinear programming problem, and I have discussed several issues to be addressed for solving the nonlinear programming problem. Let me come to that point and let me elaborate few concepts which are needed for the nonlinear programming problem one by one. Again, coming to that point, I was talking about in the last class, that whether the functions involved, that means the objective function as well as the constraints, both can be nonlinear in nature. If we consider in general all are nonlinear, then we need to study few things. First of all, whether the function is convex or concave. That's why you need to know what's the definition of convexity and what's the definition of concavity, and further issues related to that. And I told you what's the definition of unimodality. That's why modality is the next concept you need to address for solving nonlinear programming problem, and gradient of a function is another part to address. Now, today I will give you a few graphical solution of the nonlinear programming problem, and I will just show you how really the gradient and other things, convexity, concavity, all the things are related to the nonlinear program. Then you will know that yes, these are the things we need to learn, then only things will be better for learning. Now, we need to know the definition for the local optimality and the global optimality formally, that I will introduce. And as I was explaining in the last class, that if we adopt the searching algorithm for a nonlinear programming problem, the initial starting point, initial guess point is very important for us. If the initial guess point is somewhere which is far from the optimal solution, then number of iterations will be more and it will take more time to get the solution. And that's why you need to know about it. And within the feasible space, starting point, feasible space itself is very complicated in nature. That's why identifying starting point from there for infinite number of points which are within the feasible space, but that's very important. Now, you know, in the linear programming you must have learned that there are certain symptoms in the simplest algorithm where you could decide that function is not having at all a feasible solution. The solution space is unbounded in nature. But for the nonlinear programming problem, it is very difficult to identify that whether the function is the problem is having at all a feasible solution or not, whether the problem is having the unbounded feasible space or not. That's very difficult to judge, because that again the concept is that it's a very complicated in nature, the feasible space. That's why within so much restrictions, with so much complications only, we need to find out the optimal solution. Not only that, not only optimality, we have to say whether this is a local optimal or global optimal. That's why many things to be considered together. And as I mentioned, there are numerous algorithms for solving nonlinear programming problem. That's why which algorithm will be applied for which problem you need to know. Then only you will get the better solution. Better means global. And that's why let me come one by one. Now, you see f(x) equal to x square. What kind of function this is? This is a convex function, all of you know. How we can draw it? We can draw it. If you know the definition of convexity, either we can say that this function is concave upward or convex downward, or in general we say the function is convex. All right. Now, what is the definition for this? How we can say this is a convex function? The definition is that if I take 2 points from the domain, that is x prime and x double prime, and if I join the line and any value for that point, the functional value will be lesser than the any point joining these two points, any points lying on the line of joining two points. All right, that is the basic definition. How mathematically we can say, I will tell you in the next. This is a convex function. If I consider f(x) equal to minus x square, certainly it would be the reverse. That is why if I say that you must have learned in your linear programming as well, minimization of objective function is same as the maximization of the negative of the objective function. That is why if I want to get the minimum value for this object, if this is the objective function which is moving within a constrained space, then if I want to find out the minimum value of this objective function, then I can do the reverse. I will do the maximization of the minus of this function. That means instead of minimizing convex function, I will maximize the concave function. All right, and this is the f(x) equal to minus x square. This is this way. And how to define? Again, we will take two points, we will join these two points with a line, and we will see that any functional value of any point will be greater than the point of that point on the line, value of the point on that line. That is the definition of the, and this is the concave function. Either we say concave downward, that means the cup downward, concave downward, convex upward, or we say this is a concave function. That is the idea. All right, and as I said that there are 2 points, x prime and x double prime. If I take the linear combination of these two, lambda x bar plus 1 minus lambda x double bar, where lambda is lying in between 0 to 1, then the functional value will be, for the convex function, the functional value will be always the lesser than lambda f(x) prime plus 1 minus lambda f(x) double prime for any value of lambda between 0 to 1. And for the concave, that this is the reverse case. Instead of less than type, it will be greater than type, as I showed you graphically. All right. Now, look at this function. What you can find if I ask you whether the function is concave or concave? Can you say? Not really, because function is very complex in nature. There are several combinations of convex function, concave function, and you know the point, inflection point, all the points are there. That is why if I consider this range, not really we can say that this is either convex function or concave function. That is why you must expect the nonlinear programming problem where the objective function can be convex, whether the objective function can be concave, and it may happen the function neither concave nor convex, even for the constrained function as well. The same logic holds. All right, we cannot say anything. That is why there are certain important facts you need to learn. This is you will ask me why we will learn the convexity, concavity. Is it at all important for the optimization? It is really important, because just you remember the fact, we will prove it later on. I will show you how we are reaching to that point. That is a very important fact in convex optimization, is that if we considered the objective function as convex and the constraint function as convex as well, and if we want to minimize the objective function, always we will get the global minimum. And this is a reverse case for the maximum problem. If the the objective function is concave, constraint function is convex, if I want to maximize the objective function, always we will get the global maximum. That is the beauty of learning convexity, concavity of nonlinear programming problem. But as I said, that if we have the other combinations, that means objective function is concave, the constraint set is convex, and we are minimizing the function, then do not expect that you will get the global optimal solution out of it. It may happen the objective function is neither convex nor concave, constraint function is neither convex nor concave, do not expect that you will get the global optimality. It may happen that you will miss the global optimal solution in the search process. You have to be satisfied with the local optimal solution. That is why this is very important fact for nonlinear programming problem. If you remember this fact, then very easily you can say, looking at the functions in the nonlinear programming problem, you can declare, at least for certain cases, you are achieving global optimal solution, which is our ultimate target. All right. Now, you need to know what is the definition of the local optimality, global optimality, etc. Because I mentioned many times I uttered the term local optimal and global optimal. That is why let me tell you. Now, a point within the domain of the function, the point is x star. I can say that this is the local minimum point if in the neighborhood of that function we won't get any other value which is better than that. Better in the sense that we won't get any functional value which is lower than that point. Okay? Then we can declare that that is the local optimal point. That is why we are taking the point x star and we are considering the h neighborhood of that. H can be positive, h can be negative, and you see the functional value is always greater than f x star. That is why at that point there must be a local optimal point. All right. Similarly, we can extend this idea for the local maximum. The case is reverse. If I consider x star as a local maximum point, in the neighborhood of that point we won't get any point where the functional value is better than that, that means a higher than that. Always all the functional values in the neighborhood of that point will be lower than that, lower than the functional value at x star. Then only we can say x star is the local optimal. But what about global optimality? If we extend this concept from the local to global, then we can consider the whole domain of the function. If I say, instead of taking the neighborhood of that point, if I consider in whole domain of the function, no point is giving the better value for the function f, then that can be declared as the global optimal. Now, whether greater than or less than, that depends whether we are considering the minimum or maximum. That is why let me extend this concept for global optimality. Just you see, a function of one variable, everything we are considering now, I am just trying to explain you all the concepts with a function of single variable, so that very easily we can extend it for function of two variables. All right. Now, you see the function is having the global minimum at the point x equal to x star if f x star is lesser than equal to f x for all x in the domain of the function. That means no point gives the better value for f in the minimum case. All right. Similarly, for the global maximum, no point in the domain of the function you are having the higher value of the function than f x star, then that is the global optimal. Then which one is the point of inflection? All of you know. In the point of inflection, in either side of the point the function is increasing, either both increasing or both decreasing. With the figures I will show you at which point in the next class. I will show you at which point we are getting the for function of one variable, two variable as well, when we are getting the global maximum, when we will get the local maximum, when the point of inflection is coming, etc. All right. Now, we are moving to the graphical solution of the problem. Now, you see this is the objective function. Objective function is linear in nature, minimization of 2x plus 3y subject to x square plus y square is equal to 1, and x and y all are moving within 0 to infinity. Then how, if I draw the function, how it will look like? The constraint would be a circle again, and your objective function is a line. Let me draw it. This is the constraint set, but you see I have considered only the x y greater than equal to 0. That is why minimization, let me just modify the problem that x and y both are unrestricted in sign. Let me consider that x and y both can move from minus infinity to plus infinity, as you did for linear programming as well. You must have considered the set of variables which are unrestricted in sign, and you know how to handle that in linear programming problem. But in nonlinear programming problem also we do the similar process, but for the time being, for graphically explain to you, let me relax these constraint that x y is greater than equal to 0. Let me say x and y is unrestricted in sign, that means both can take minus value and positive and negative value whole, then this is the constraint set for us. Okay. Now we are trying to find out the minimization of 2x plus 3y. Now my line is moving, this is f x equal to 0 at point x equal to 0, y equal to 0, alright. Now the function moves this way, if I move this way functional value will increase, and if I move this way the functional value will decrease, alright. That you know from your mathematical knowledge. That is why if I move this way f x equal to 1 functional value is increasing, I will be further from the minimum point. That is why my direction must be the reverse one. That is why if I move from here further and further, then at this point at minus 0.55 and minus 0.83 we will get the minimum value of the function f. And you see, I will explain you a few things here with the same example. As I said that the gradient is very important for getting the optimality, optimal point, maximum point or minimum point. That part I will just explain you with this example. Now this is my constraint set. I am considering the previous example as well. Now what about the gradient of the constraint set? You know always the gradient would be this way, because if I at any point the gradient would be directed to the outside, because if I consider the tangent, then normal to that tangent would be the gradient, as you know. That is why these are the gradient at each and every point on the constraint space. These are all x, alright. Now this is the gradient of the objective function. As I said that if I move this way objective functional value will increase, and if I move this way the objective functional value will decrease, alright. That is why the gradient of the objective function will be this way. And you know how to find out the gradient of a function. If I consider the function of two variables, at any point the gradient of the function would be the partial derivatives of the function at that point. That is why I will consider del f by del x, del f by del y, and at that point whatever value will come, that would be the gradient of that function. That is why this is the gradient of the objective function, alright. And this is the gradient of the constraint. Now you see how we are getting the relationship between the gradient of the objective function and the gradient of the constraint at the optimal level. Now you have achieved the minimal point here, alright. Now what did you see? This is the gradient of the constraint and this is the gradient of the objective function at this point. What did you see? At the minimum point, the gradient of the objective function and the gradient of the constraint all are moving in the reverse direction. We will see, when we will see the nonlinear programming problem, we will just give you further conditions and a further theory. Then we will establish this fact that always at the minimum point, gradient of the constraint and gradient of the objective function would be in the reverse direction. But if I consider the maximum of that function, that means function is moving, and that should be the maximum point, because if I go further with the function, then I will be beyond the objective function space. That is why this is the maximally I can move at that point. Then this point must be the maximum point, and the coordinate of this point would be the reverse one, the 0.55 and 0.83, so like that, okay, as minimum we got. And what did you see here? Gradient of the objective function and the gradient of the constraint all are in the same direction, okay. That is the important fact again for the nonlinear programming problem, that gradients are reverse in the minimum point and gradients are in the same direction in the maximum point. This is very important in nonlinear programming problem. You just remember it. We will establish further. Now let me the thing with other example. The same thing I will explain to you, but the problem is little bit complicated because here we have considered both the constraint set as well as the objective function, both are nonlinear in nature, but few constraint I have considered the linear in nature. All right. Now, let me draw it. This is my problem. Now, let me draw the function. Now, if I draw it, then this is the line x minus y is equal to 1. This is another line x minus y, x plus y is equal to 1. Surprisingly, this is the negative image has come. Okay. This is the function x square plus y is equal to 1. All right. Now, this is the objective function because forget about this big, if I draw it, all of you are understanding. These are the reverse images, somehow we got it. Now, this is the constraint set and the points are the feasible space is combination of those points which are being satisfied with all the constraints. That is why I can say this is my feasible space. All right. Again, I am relaxing x and y from negative and positive, otherwise we won't get this feasible space. I want to show you the bigger picture, that is why I am relaxing this fact. All right. Now, what is my objective function? Objective function is again another parabola for us. These are the points, the intersecting points for us. Now, this is the objective function is moving. That is why, what is that? Function problem is minimization problem. That is why if I move this way, then I will get the better value of the objective function. If I move in the lower side, I will get the lower value of the objective function. That is why gradient this way, and since this is a minimization problem, I will just move reverse to the gradient direction because that will best satisfy me. I am searching for the minimum value. Now, you see, if the function is coming down and down, if I come this point, I am out of the feasible space. All right. I do not want to be, that is why certainly that must be the optimal solution for this problem. If I relax the non-negativity constraint, then only, and my optimal solution is -1, -2. Here also, if you just this is the task of yours, that just to check whether at the minimum point you are getting the gradient direction for the objective function and the constraint both are in the reverse direction or not. Okay, that you check. Now, whatever we have seen till now, what are the things we have seen? There are few things to be remembered, that you see there are we need to consider the constraints. Constraints can be linear, constraints can be non-linear, constraints can give you the discrete feasible space, constraint can form the continuous feasible space. That is very important for us. Now, the next thing we need to consider the nature of the design variable. In some time it may happen design variable means the decision variable. Sometimes it may happen that the decision variables are all discrete in nature. That means the decision variable can take either 0 value or 1 value. You must have done the integer programming problem in linear programming course, that this decision variable can take the discrete value. For example, the problem is till now I did not consider any real life problem, but you must have come across in the linear programming problem where we need to decide for certain situation how many chairs I have to produce in my factory. That means the decision variable must be integer in that case. That means if this is the case, that is very important. That is why even in the nonlinear programming problem, if my design variables are discrete in nature, how to handle it, that is very much important. Now, what about the nature of the equations? What are equations are involved? That is very important for us, because you know, for the nonlinear programming problem, nonlinear function can be of different type. It may happen that nonlinear function is in the fractional type. For example, if I consider the function can be this way, function of two variable, if I consider x square plus y divided by x minus y, minimization of this or maximization of this. You see the function is of fractional type. That is why how to handle this one. Now, it may happen the function is separable in nature. For example, x square plus x cube plus y square plus y cube, there is no term like x y. That means I can separate x in one side, I can separate the function of y. Then how to handle this? If x y is coming to this, then it is not a separable nonlinear programming problem. How to handle that kind of problem? That is why in the next class I will talk on the classification of the nonlinear programming problem. Depending on the nature of the constraint, nature of the design variable, nature of the functions involved, nature of the permissible design variable. Another thing is very important, the decision variable which are involved in the function that may be that may have the stochasticity. That means it may follow certain probability distribution. In that case, how to handle that? There is a separate branch in nonlinear programming problem that is called the stochastic nonlinear programming problem. That is why depending on the stochasticity, depending on the deterministic nature of the design variable, how we can categorize the nonlinear programming problem, that also I will talk in the next class. Now, what about the separability? As I talked about it, there is a separate branch of nonlinear programming problem that is called the separable nonlinear programming problem. Sometimes the nonlinear programming problem is called as a geometric nonlinear programming problem. And the beauty of the nonlinear programming problem is that, as I was mentioning, different kind of nonlinear programming problems, all are having different algorithms to solve. That is why there is no one solution process like your simplex in linear programming, that you will apply that one on any kind of nonlinear programming problem, you will get the solution. That is why you need to learn all kind of algorithms separately. I will talk about that. And the last point that is very important also in real life situation, it may happen we may not have one objective function. Like whenever we are considering the minimization of objective function, generally we are considering the cost function. Whenever we are considering the maximization of objective function, we are considering the profit of objective function, or we are considering the goodwill of the firm. That is the objective function that we are trying to maximize. It may happen both the objective functions are together. That means we are trying to minimize the cost of a certain product, as well as we are trying to maximize the profit. Is it at all possible? Shall we get any optimal solution from that complicated situation? There is a separate branch on that, that is called the multi-objective nonlinear programming problem, that not really is within the syllabus of yours. I will deal with the single objective nonlinear programming problem in the respective classes from the next. Thank you for today.